Alright, hey, it's been a while since I made a video, and I've been having a lot of fun this summer. I've been learning some new things, trying some new things, dusting off some old things, and about 10 years late on this one, but I finally understand a bit about Docker and why Docker is so useful and so interesting, and so I've been digging into that for the past few weeks, and I may do a video at some point going into some of the things I've learned. But today I want to use Docker to deploy a couple of legacy cell matrix applications that I've dusted off and also improved on. The first is the graphical cell matrix loader, the way that we can edit and create circuits graphically using drag and drop and such. And then a modern version of the cell matrix simulator written in Python, which I've also ported into Jupyter Notebook with a custom kernel to make that more accessible. But anyway, let's take a look at how this plays out in Docker. So the loader, is driven from a YAML file, and pretty straightforward, right? So this is already on Docker Hub. Prime Minister 37 cmloader gets you the image. There's a bit of wonkiness around getting GUIs to work. After I spent quite a while figuring out the basic nuts and bolts of Docker, I tried to switch over to doing some GUIs and found out that seems to be a bit of a not quite what it's made for spot with Docker, but you can get it to work. In particular, you have to set up the display, obviously, but also copy this directory, your X11 Unix, to get the magic cookies in place. But anyway, running this is just a Docker compose. Plus setting up the xhost, right, to give access for the X information. So yeah, just specify the YAML file and run cmloader. And I've already downloaded this one, so it's already installed it. But if you do this the first time, it goes through the usual install steps. And here's our cell matrix layout editor window. So the version I have on Docker comes with some pre-existing libraries and grid files. So if I come under grids, for example, I can find some examples of some memory circuits that I've created. I have some stuff for playing around with DS encryption, and so this tool is basically just a drag and drop way to create cell matrix circuits. Each of these boxes is a single cell matrix cell, and heavily keyboard driven. There's shortcuts in here, but I'm just going to Control E to edit. And so here's a description of what this cell is. It's called E, and it copies from the west to the east, and there's a little icon, and you can actually take these icons and throw them into an editor and make changes to them and load a new icon. And then if I save that, that icon will appear anywhere that I have that symbol, but I'm not going to save it. You can rotate cells, so this is a Control R to rotate, and it will adjust the truth table accordingly. I can take a collection of cells and rotate all of them, or I can rotate the whole group to actually take a multi-cell circuit and move it around. I can also take a cell and copy it. I can paste it as usual, but I can also do what's called an OR paste, which pastes it on top of a pre-existing cell and combines their truth tables and also combines their icons. It's a drag and drop based system, but it's actually pretty efficient once you get good at it. I used this around 2000, beginning of the century, to design what we call the supercells, a 270 by 270 cell circuit. So pretty large scale and very easy to to do once you kind of get the hang of this. You know, you can just start putting stuff together. And so let me go through an example of this and see how we can actually use this to build something meaningful. Also, once we have this done, we can save the grid file. We can also save a binary grid file, which we'll be able to load into the simulator. So I'll do all of that. But let me go ahead and run this from scratch, and let's open up under libraries, under let's see, maybe not under libraries, ALU. Let's open ALU.grid. So the only thing I want from here is this one particular cell. This is a general purpose add block. So it basically takes one value from the north, one from the south, takes incoming carry from the east, produces a sum to the south, and an outgoing carry to the west, so you can cascade these. So data north is A, south is B, east is carry in, west is carry out, south is sum. But it also has some extra hooks. This was part of an ALU circuit I made, but I just want to grab this one cell right here, and I'm going to copy it and just paste a few of these down like this. So I'm going to make a 2-bit adder basically, and I'm also going to open a grid that's just called useful cells, and this is just a collection of useful cells. And so what I want to do is feed in a 2-bit number up here and feed in another 2-bit number here and get a sum coming out of the bottom. So I'm going to grab this piece of wire, copy it, paste it, rotate it, copy it, paste it over here. I'm going to take a corner, copy it, paste it here, take this, paste it, rotate it. There's our least significant bit. I'm going to take this whole thing and I'm going to paste it right here and replace this cell that I just blew away. So there's my 2-bit number coming in on top, and now I need to feed another 2-bit number into the bottom. So let me go ahead and start that here, and I'll take a different wire to rotate that. This will be least significant bit, most significant bit. I'll put that right there. And then this one I'll copy and I'll just or paste that on top. So now I have my second number B, bit 0 goes in here, bit 1 goes in here, and then let's just take the output and send that down to the bottom. So we'll just or paste those, and so there's our add test circuit. So let me grab this. This looks like it's 5 by 4 or 6 by 5. So let me make a new grid, 6 by 5, and let's paste that, and let's save this. So we'll save the grid as, and I have a shared area, and this is all, you know, containerized inside Docker, but anything I save in the shared area will also appear in the directory from which I ran the Docker. So let me save this as add test.grid, and so if I come in here and I look, I've got an add test.grid now. And so let me go ahead and also write a binary grid, and I would call this add test.bin. Nope, no, put that in the wrong directory, so let me do that again. Let me save it under shared, add test.bin, and there's our add test.bin, and this is one of the new hooks I just put in. It also saves the icon information, and our simulator is going to be able to use that so that in the simulation we can actually see this picture to help us know, you know, what's supposed to be going on in the circuit. So that's the cell matrix loader, and there's documentation available. I'm going to open up the GitLab repository, which includes the documentation, and I'll put information for that in the video description. But let's go ahead and exit here, and let's go on to the cell matrix simulator. So here's the YAML, and basically the same as for the loader. And so we'll just bring that container up. And there's our current matrix. It's a 1 by 1. And this is all command line driven, so we can do question mark to see a list of legal commands. And by default, this is a 1 by 1 matrix, so I can set 0, 0 data west, and it turns big to show that there's a 1 coming in on that. I can say set 0, 0 data north, and there's a 1 up there. I can also interact with this with the mouse, so left click will toggle the input, a right click will toggle the C input. I can click in here to see the equation that's stored in a cell. I can also say dump to see the equation. I can say truth table row column to see the truth table, and I can compile 0, 0. Let's make a wire data east equals west. So now if I say dump 0, 0, it tells me, hey, 0, 0 says take the west, send it to the east. If I put an input on the west, it comes out to the east. So, this is all standard cell matrix, and there's some tutorials I put together under Jupyter to expose people to this and so on. But let's go ahead and play with that 2-bit adder that we just created. So I can say load 0, 0, and I'll do shared / add test.bin. And it'll tell me that's a 6 by 5 grid file, and since I'm trying to load it at 0, 0, I need a matrix that's 6 by 5. My current matrix is only 1 by 1, so let's just reinitialize our matrix, go back and load in our adder, and it not only loads in the Boolean equations, but it also loads the icons, so I can send information in here and so on. So right now there's the number 2 going in on the top, and if I send in the number 2 on the bottom, which would be right here, that comes in there. 2 plus 2 should be 4. So remember, I mentioned this is a funny circuit. It needs to have a 1 coming in on the left to turn this adder on so that it actually does addition. So this is cell 2, 2. Let's compile 2, 2 and just say data east equals 1. And now we've got a 2-bit adder. So 2 plus 2. But I copied the wrong cell. Because this is not an adder. I actually copied a cell that's just supposed to invert the number coming from the top. So let's quit out of here. Let's go back and run the loader, and let's make a quick correction to that. So let's open the grid, and we will open add test.grid, and then let's go back to our ALU, and this is actually the cell that's a 2-bit adder, right? So I copied the wrong one, so let's copy that, let's paste it here, and let's go ahead and put that put a cell in there that outputs a 1 to the right, just so that we don't have to do that ourselves. So let's paste this here, and now we'll save this grid, and we'll rewrite the binary grid, and we'll put it in shared, and we'll go to add test.bin, and we should be good to go. Let's go ahead and run the cell matrix simulator, and this is all run under RL wrap, so we can go back and reinitialize the matrix and reload our file, and now we should have a full-blown 2-bit adder. 2 plus 2 is but made another typo. And this third bit of the sum comes out from the carry out of this second stage of the adder, but I forgot to route it down to here. But we can see 2 plus 2 is 4. 2 plus 3 is, there's a 1, 0, 1 is 5, and so on. So, rapid development, this is your key, right? Let's go ahead and fix that wire. So we'll reopen add_test.grid, and let's go back and open useful cells. And we want to take this carry that's coming out of here and route that down to the south. So let me grab a little piece of wire, and again we will OR paste that, and then let me grab a straight line and let's OR paste that. So now what's coming out of that carry from the final stage will come down as our third output bit. Let's save that. Let's write the binary grid. Save it as add test and get out of here. So final test now. Run the simulator. Initialize the grid. Load the circuit. And finally 2 plus 2 is equal to 4, 1, 0, 0. 3 plus 3 is 6, 1, 1, 0. 1 plus 1 is 2. 3 plus 1 is 4, and so on. So that's a few iterations of you know, sort of the design, develop, test, debug, redesign kind of cycle that you run with this stuff. If it looks terribly cumbersome, it is terribly cumbersome to begin with. Once you get used to it, it's pretty fast development. And so the loader and the simulator, you know, originally 25 years ago were pretty separate entities, and this sort of brings them more into harmony with one another, so we can actually like see the results of, you know, the design we've done in the loader in here and use that to help us debug and so on. And you know, I'm doing a lot of point and click here, but this can all be driven from the command line. I can say clear 0, 0 data west to clear this input line. If I want to change this from a 1 to a 0, I can say clear 1, 0 data west. If I want to take this cell right here, I can say set 4, 0 data west and turn that on. So now I'm doing 3 plus 0 and so on. And if we go into C mode, so if I right click here, you know, I can look at 00's truth table, and there's the truth table for a wire. But if I start ticking in zeros, I can see that the bits that were stored in the truth table are coming out here. And as I load this in, you know, I'm obliterating those zeros, those ones with zeros. And if I set my D input to be 1 on that side and I start ticking in values, I will begin flooding my truth table with 1s. And then when I leave C mode, this is now, you know, doing whatever truth table I just loaded in, which is this random collection of 1s and 0s. So, you know, it's a full-blown cell matrix simulator. You don't need the loader to use it, but you're able to, you know, play around with D mode and C mode. And like I say, I have a Jupyter notebook with a custom cell matrix kernel that supports all of this, and I've got the start of a tutorial, and I'll talk about those in a different video. Anyway, Docker happiness for me, so so that's been fun. All right, take care. Bye.